The topic of this lecture will be carbon 13 NMR. Carbon is the most common nucleus that we study with NMR after protons. 99% of carbon is the carbon-12 isotope. Carbon-12 has an even atomic number and an even mass number, which means that it has no spin. It is therefore NMR invisible. 1% of carbon is the carbon-13 isotope. Because this has an odd mass number, it has a spin and is NMR active. However, because it only makes up 1% of the carbon found in any given sample, the signal that we get for carbon NMR is very weak. This has some important consequences for carbon NMR, making it different from proton NMR. First, we can't use the integrations. The integrations don't work like they do in proton NMR, and therefore they're not proportional to the number of carbons that a peak stands for. The second main difference between carbon NMR and proton NMR is that we don't normally see splitting. Again, this is a direct consequence of the fact that there is only 1% of carbon-13 in a given sample. What this means is that the data we can get from a carbon-13 NMR spectrum is the chemical shift of the different carbons in the sample and the number of signals, the number of different carbons in the sample. The relative chemical shifts of carbons in different functional groups can be seen in this figure. Let's see if we can use the shifts in this table to assign the carbons on a new molecule and its carbon NMR spectrum. Let's consider this spectrum. This spectrum has 5 peaks in addition to the peak due to TMS at 0, and those are representative of the 5 carbons in the molecule. I'm going to letter my peaks just like I do with a proton NMR, going from lowest shift to highest shift. Now let's try to assign these peaks to the structure of this molecule. The easiest peak to assign is peak E. This is going to be the peak that corresponds to the carbonyl carbon. The next highest peak, peak D, is going to be the carbon that is attached directly to the oxygen. From our figure above, we can see that this is exactly where we would expect a carbon single bonded to an oxygen to show up in a spectrum. Peaks A, B, and C are all within the alkane range of the carbon NMR spectrum, but we can assign them based on how close each carbon is to the electron withdrawing functional groups. Carbon C will be directly bonded to the carbon of the carbonyl carbon. Carbon B will be directly bonded to the carbon that is single bonded to the oxygen. And carbon A will be furthest from the functional group and therefore the least shifted. Now let's use this figure of NMR shifts for carbons and try to predict the carbon NMR spectrum for a new molecule. Now we will try to draw the carbon-13 spectrum of T-butyl methyl ether. T-butyl methyl ether has 3 types of carbons, so we should expect to see 3 signals in the carbon-13 spectrum. It has the 3 methyls on the T-butyl group that are all equivalent. It has the methyl on the other side of the ether, and it has the central carbon of the T-butyl group. Now using the figure above, we're going to try to predict where the shifts of each of these carbons will fall. Carbons A should fall in the alkane region of the spectrum, about 0 to 40 ppm. Carbons B and C are directly bonded to oxygens, so they should fall in the range of the spectrum of about 50 to 90 ppm. However, we wouldn't expect these 2 carbons to have the same shift. Carbon C is directly bonded to 3 carbons, while carbon B is directly bonded to 3 hydrogens. Because carbon is more electron withdrawing than hydrogen, we would expect carbon C to be shifted downfield relative to carbon B. Now let's look at the carbon-13 NMR spectrum of T-butyl methyl ether. We see that this spectrum has 3 peaks, just as we predicted. 1 peak in the alkane region of the spectrum, due to carbons A, and 2 in the region of the spectrum between 50 and 90 ppm, due to carbons B and C, with carbon C being shifted further downfield than carbon B. In general, because we get less information from a carbon-13 NMR spectrum than we do from a proton NMR spectrum, you typically cannot predict the structure of an unknown molecule based on carbon spectrum alone. However, it can be a very useful tool in addition to other spectra, like the proton NMR or the IR spectrum of an unknown molecule, to predict its structure.